Hello, good morning dear students. Once again I am here, Lalit Kumar P. Bhaiya, Associate Professor, Electronics and Telecommunication Engineering Department, Bharati College of Engineering and Technology, Durg. Dear students, today we will go through the subject digital signal processing, and we have already seen linear time invariant systems. A lot of issues associated with linear time invariant systems we have seen. The properties and what is the linear time invariant systems, their combinations, their operations, convolution, etc. Lot of we have seen. Today we will discuss especially about the linear systems, the connection of the linear systems, what is the cascade connection, what is the parallel connection, and etc. This is all about the linear systems. We have all basic things we have already learned in this particular PPT about the linear time invariant system. But now we will go from the slide number 77, that is linear systems. I will go now here for the linear system that we will see. So let us see these linear systems.
Ready.
Here, this we have to see linear systems. A system, now you can see here, this is linear systems. A system takes a signal as an input and transforms it into another signal. Linear systems play a crucial role in most areas of science. You are already known what is the linear time invariant system, that utilizes two properties, the property of linearity and property of the time invariance, that we have already seen. Here we will see this crucial role in most areas of science. Closed form solutions often exist. Theoretical analysis is considerably simplified. Then nonlinear systems can often be regarded as linear for small perturbations, so-called linearization. And for the remainder of lecture course, we are primarily going to considering linear time invariant systems and considering their properties. That properties also we have seen. Now, this diagram is shown here. This is a continuous time system, and this is the discrete time system. Here input is x of t and here is discrete time signal x of n. Here output y of t, and in discrete time signal output is discrete output signal, that is y of n. Here examples of simple systems to get some idea of typical systems and their properties. Consider the electrical circuit example. This is the differential equation, and this is the equation of the RC circuit, which is the electrical circuit. ddt of Vc of t plus 1 upon RC Vc of t is equal to 1 upon RC Vs of t, where Vs is the input signal, Vc is the voltage across the capacitor, which is first order continuous time differential equation. You can see only d by dt is there, that is the first order differential equation, continuous time system. And this is the first order differential equation in discrete time system. Y of n is equal to x of n plus 1.01 y of n minus 1. Y of n minus 1 indicates the first differentiation in case of the y, and x of n minus 1 represent the first differentiation in case of the x, where y is the monthly bank balance and x is the monthly net deposit. This is the example from the banking side, so that's why it is written here monthly bank balance and monthly net deposit. This is the example from the system. And here y of n minus rc by r into dct v of n minus 1 is equal to k upon n into this f of n, which represents a decentralized version of the electrical circuit. Example of the second order system in terms of second d2y by dt minus plus dy by dt plus cyt is equal to x of t. This is the second order equation. System described by the order and parameters are a, b, c here. Here is the a constant, b constant and c constant, c of y of t. So this is the second order system. First order step response. Last time we have seen in linear time invariant systems, LTI systems, last time we have seen the
आगे सर फिर चला गया.
first order step response. Dear student, last time we have seen in linear time invariant systems as well as before the LTI systems, we have studied the different types of the input sequences, standard test signal. Similarly, one of the standard test signal is the step input, and we will see the step response for the first order system. We have seen the equation of the first order, equation of the second order. First order is related with the RC circuit, second order is related with the maybe a 2 RC circuit or any other system where we can derive the second order equation. People tend to visualize systems in terms of their responses to simple input signals. The dynamics of the output signal are determined by the dynamics of the system. If the input signal has no dynamics, consider when the input signal is a step at t, n is equal to 1 and y of 0 is equal to 0. So this system is given first order continuous time differential equation is given by dy by dt plus ay of t is equal to u of t minus 1. This u of t minus 1 is the step signal delayed by one sample. This is u of t minus 1, that is delayed by 1 unit of time. And this is differential equation, first order differential equation for the discrete time system, which is y of n into 1 plus ak minus y of n minus 1 is equal to k into u of n minus 1, where u of n minus 1 is the step response, or you can say it is a sample sequence delayed by one sample. This is the sequence given here for this equation as a discrete time system, and this graph you can see for here for the continuous time first order system. It is a graph shown here. System linearity. This diagram you can show with the help of this y axis and x axis. This linear graph is shown here. This indicates that the linearity. The most important property that a system possesses is linearity. This one. It means allows any system response to be analyzed as the sum of simpler responses. So, what the linearity means, if the input is linear, the output must also be linear. Of course, the linear time invariant systems, LTI systems, exhibits the property of the linearity. That's why here it is used as a linearity. Then convolution. Convolution we have already seen, circular convolution, linear convolution. So linear convolution is the best example of the linear time invariant system. That is a tool in the DSP that we have already studied. We have also seen the problems on the linear convolution as well as the circular convolution. Specifically, a linear system must satisfy the two properties that we have seen, additive property and scaling property. Any linear time invariant system or linear, I mean to say here the linear system Linear time invariant system satisfies the two properties of the linearity and property of the time invariancy. Similarly, any linear system satisfies these two properties, additive and scaling. Additive means this x1 of t plus x2 of t. The response is y1 of t plus y2 of t. Linear combination of these two input is the linear combination will give the linear combination of the two outputs. Similarly, scaling, you can scale here by a into x1 of t. Its response will be a into y1 of t. This is called as the scaling. Scaling means to multiply with some scalar that is constant. That is called as scaling. And combination of this additive and scaling will make a linear system like this: a into x1 of t plus b into x2 of t. Then its response will be linear. That is a into y1 of t plus b into y2 of t. And example for linear is y of t is equal to 3 star of x of t. This is the example of linearity. You will get the response like this. The scaled by 3, factor of 3 here. So y of t is equal to 3 star x of t plus 2 is also this is a non-linear because it is added 2 here. So this response will be non-linear. You can see this is the response that will be non-linear. And equivalent definition for discrete time system can also be seen. Here, bias and zero initial condition. Already in electronic circuits and electrical circuit, we know what is the initial condition and what is the zero initial condition. At the charging of the capacitor, we write the equation for the charging of the capacitor. We may consider initially the capacitor is discharged. So we can put the voltage across the capacitor initially at t is equal to 0 is equal to 0. That means this is called as the initial condition. So similarly, we have the bias and zero initial conditions while solving these differential equations for a linear systems. Intuitively, a system such as y of t is equal to 3 into x of t plus 2 is regarded as being a linear. However, it does not satisfy the scaling condition. This is the scaling condition here. There are several similar ways to transform it to an equivalent linear systems. So here, perturbations around operating value x star and y star. These perturbations are given sigma epsilon x of t, epsilon y of t, and using these perturbations, deviations, we can calculate the values. Similarly, linear system derivatives dy t is equal to 3 dx of t are the linear derivatives, and this graph can be shown with these perturbations. Locally, these ideas can also be used to linearize a non-linear system in small range. Linearity and superposition. One more very important thing, dear students, as already we have seen and you known the principle of the superposition. So linear time systems, linear time invariant system also uses the superposition along with these two properties, that is property of linearity and property of the time invariancy, and the additive property and scaling property. So rather than this additive and scaling property, it also uses this superposition principle. And you know in electrical circuit very well what is the superposition theorem. Similarly, here we apply the superposition theorem. Suppose an input signal x of n is made of a linear sum of others. This is called as basis of simpler signals except k of n. X of n is equal to summation k to, let us say, some value here, ak x of kn is equal to a1 x1 of n, a2 x2 of n plus a3 and so on, plus this a. Then the linear system response is in similar way. The response of this input will be y of n, and this y of n is equal to summation k, ak yk of n is equal to a1 y1 of n plus a2 y2 of n plus a3 y3 of n and so. The basic idea is that if we understand how simple signals get affected by the system, we can work out how complex signals are affected by expanding them as a linear sum. This is known as the superposition property, which is true for linear systems in both continuous time as well as the discrete time. Important for understanding convolution sum, we use this linear time invariant system, this property of the superposition. So this superposition is important in case of the linear time systems. Definition of time invariance, that already we have seen. If there is a change in the time in the input, the same change in the time at the output occurs, then it is called as a time invariance. But if there is a change in time, suppose x of n minus 1 is the change in the time at the input, and you will get the y of n minus 2 at the output, then it is called as a time variant. So a system is a time invariance, its behavior and characteristics are fixed over time. We would expect to get the same result from an input and output. From an input experiment, if the same input signal was fed in at different times, example, the following CT system is time invariant. Y of t is equal to sin x of t, because it is invariant in a time shift. Time invariant is also called as a shift invariant. This is also called as a shift invariant. This is x2 of t is equal to x1 of t minus t0. This is called as a shift invariant, and it is variant because it is varied by a time t0. And because the system parameters that multiplies the input signal is time varying, this can be verified with substitution. These examples are given that we have already seen for the substitutions and etc. System with and without memory. This is some systems requires the memory for the operations and memory for storing the particular results, and some system does not require the memory. It operates only in the accumulator, and therefore what happens? Some differential equations where constants and multiplications are required. Like if we use the convolution sum sometimes requires the large memory also to store the products, and after storing the products we get the sum. So we need the memory. But some operations, like supposed to be a y of n is equal to twice x of n. This operation does not require the memory because it will be calculated in the accumulator itself, and hence no need of to store the memory. Therefore, this is called as the system with and without memory. It's just like you can see this equation: y of n is equal to twice x of n minus x square of n whole square. So this no system dynamics here, and here we don't need the memory because this is the present input x of n. This is also the present input x of n. So it is the operation on the present input, hence we don't need to store the memory. Example, a register is a memory-less continuous time system where x of t is current and y of t is the voltage here. A discrete time system with memory is an accumulator, that is integrator. For discrete time system, we have these summations to integrate it, x of k, and y of n is equal to x of n. X of n minus 1 is the delay unit. Roughly speaking, a memory corresponds to a mechanism in the system that retains information about input values other than the current time. So this equation given for the current situations. This is memory less situations. Causality. System causality. In previous lectures, we have seen what is the causality. For the causality for the signal, what is the causal signal, and now we will see here what is the causal systems. What is the causal? Causal means the response, that is output depends upon the present and the past input is called as the causal systems. Those systems which are causal, having their response which depends on present input as well as the past input. There should be no future inputs at the output of the causal system. If, like, supposed to be a y of n is equal to x of n plus x of n minus 1, then it is said to be a causal system, because y of n is dependent upon x of n and x of n minus 1, present and past inputs.
Continue, sir.
Then causal systems, so past and present input, y of n is equal to x of n plus, let us say, x of n plus 1. This is a non-causal, anticipatory, we call it as anticipatory, non-causal system, because here x of n plus 1 is available, and therefore this is called as a non-causal system. Similarly, system causality can be defined, and we will get the in place of this we have already seen derivation of the how the system is causal in terms of the h of n. H of n must be less than 0 for system to be causal, that we have already seen and proved for the causality of the system. So here this causality is important for the system. And lastly, the stability. These two properties of the causality and property of the stability of the system, we have already seen. What is the stability? Roughly I can say that stability means bounded input, bounded output. The system is particularly called as Vibo stable system, that is bounded input and bounded output system. For any system which has a bounded input means have a particular input to a particular limit only, must get the bounded output, that means a limited output, and means a particular response to a bounded value. This is called as a stable system, and we have already derived the condition for the bounded input and bounded output stability. The same thing is explained here for the bounded input and bounded output system. Let us say mx is the bounded input having a finite value mx. So we must get the finite value, let us say my is the output, finite value. So for bounded value we have a finite bounded input, we have a finite value of the input, and for the bounded output we must get the finite value of the bounded output. Then the system is said to be a stable system. This is the example given for the first order system for the RC filter. For a stable system, if we consider the value of resistance and capacitors, and this is the invertible and inverse systems. This is also, we have seen, it is a simple thing. Inverted systems means if we consider about the x-axis and y-axis, at the first quadrant and at the fourth quadrant. The first quadrant value can appear at the fourth quadrant, called as the invertible systems. So this invertible systems is also possible. This type of principles are used in encryption and decryption. Systems control where the reference signal is input. So this signal encryption and descriptions are used. And finally, for today's video, I will also tell about this complex exponential. Complex exponential plays an important role while linear systems. While analyzing the linear system, we can consider the complex input like e to the power j omega n. E to the power j omega n is the complex input for the n number of inputs, n number of samples. If we consider this complex input, then we will get the frequency response, magnitude response, as well as the phase response. So this is the today's lecture about this linear time invariance, linear systems, where we have seen. Next time we will go for the another concept of the linear time invariant system. Thank you very much for listening this video. Thank you very much.